So for this topic, we're going to look at the polysaccharides. So from the word poly means many molecules of the monomer joined together. So when you look at these polysaccharides, they are polymer, or more precisely, they are macromolecule according to our definitions, because when we talk about polysaccharides, we look at the condensation process of thousands of the monosaccharides. So what is the definition of macromolecule again? When you look at the words macromolecule, basically means that they consist of many repeating monomer. So in this case, polysaccharides, their repeating monomer is glucose. Second, this repeating monomer must be either identical or similar. So in polysaccharides, this repeating monomer, which is glucose molecules, they are identical. Okay, and they are joined side by side by the process of condensation. Can you see that? So that's why polysaccharide is a macromolecule. So these monosaccharides, they are linked by glycosidic bonds. And if you look at these polysaccharides, they are not sugar anymore, and they are insoluble in water. So highlight this is a very important properties of polysaccharides. So polysaccharides, they are not sugar, they are insoluble in water. So therefore, they are not lower down the water potential. So try to imagine that this is our cells. When we absorb the glucose, glucose is water soluble. So when they are water soluble, they enter into our liver cell, for example. If we store them as a glucose, accumulation of glucose, we're going to lower down the water potential. We learned about this, right? The presence of the solutes lower down the water potential. So when you lower down the water potential, what will happen next? So you will see osmosis take place, lysis of the cells take place. So in order to prevent the lysis of the cells, we have to convert the glucose into these polysaccharides, for example, glycogen or starch. Therefore, the cells won't burst, particularly in animal cells, we convert it into glycogen, okay, as well as in the plant cells, we convert it into the starch. So the most important polysaccharides that commonly occur in nature, we do have the starch. Starch is not a pure compound. Actually, it consists of amylose and amylopeptin. We're going to look at the glycogens as well as cellulose. So all of them, they are polymer of glucose. And if we want to get back the glucose, we can use the enzyme-controlled hydrolysis reactions. Okay, so we can write down amylose, amylopeptins, alpha glucose, they're monomer, glycogen, alpha glucose. Cellulose, we use beta glucose. So we need to know how the formations of the amylose, amylopeptins, glycogen, as well as cellulose. Okay, so we're going to start the first part, which is the starch. So when talk about the starch is digestible, means that we have the enzyme, okay, amylase, for example, okay, which consists entirely of highlights alpha glucose molecule. So they only have alpha glucose. So when talk about starch, there's a mixture of amylose and amylopeptin. If we look at the structure, or in the if we look at percentage, amylose roughly about 20 to 30%, but amylopeptin about 70 to 80%. So they are the mixture. So if you look at the structure, you can find the starch in a starch granule inside the chloroplast. Can you see that? The starch granule inside chloroplast. So when you enlarge it, you can see that you have the amylose and amylopeptin. So what is the main difference between amylose and amylopeptin? You can see the amylose is a single unbranched change, which at helical structure. Can you see that helical structure like this? Amylopeptins also the same. You can see that's helical structure, but they have branches. Okay, so amylose is the unbranched molecule. Amylopeptin is a branch molecule. So we're going to look at how amylose can be formed as well as amylopeptins can be formed. So if you look at the amylose, amylose is a long unbranched change of several thousand alpha glucose joined by alpha-1,4 glycosidic linkage. If you compare the amylose, because they form this helical structure, So therefore, we can pack them nicely. So they have the very compact shape of amylose. When the change actually form this helical structure. And the helical structure is due to what? It's due to this alpha-1,4 glycosidic linkage. Okay, because the alpha-1,4 glycosidic linkage actually promotes the formations of these helical structures. Okay, so basically, if you understand the concept, how we form the maltose is the same. So it means that once we form the maltose already, so this is the maltose. Right, so glycosidic bond, so 1,4. So we join another one and then continue. Then this is, okay, a single unbranched change of the amylose. Okay, are you clear? So continue. So it will consist of alpha-1,4. So alpha-1,4 will give us a single unbranched change. And also because of this alpha-1,4 glycosidic linkage, it make this molecule actually turn into the helical shape. So let us look at how this helical shape actually take place because of the extra forces here. So what's the extra forces? The hydrogen bonds formed between the oxygen atom bound at the carbon number 2 of 1-glucose and the hydrogen atom bound at the 3rd carbons of the next glucose molecule. So if you look at the diagrams here, hydrogen bonds in the amylose molecule, so use a dotted line completes a figure 3.5 by drawing the hydrogen bond. So now you can see something here you have to understand. This is below the ring, the OH group below the ring, the H below the ring, OH below the ring, H below the ring. So what will happen here is the O is delta negative, correct or not? H is delta positive because O take the H, the electrons nearer to them, so therefore H delta positive. And because of this, they form the hydrogen bond. So hydrogen bond actually is a dotted lines, okay? You use a dotted line to form the hydrogen bond. So you try to imagine, guys, you have the extra force at the bottom of the ring, okay? Below the ring, upper part of the ring, no hydrogen bond is formed. So means that it tried to pull the molecules nearer because of hydrogen bond. Try to imagine that, guys. You try to imagine, you have a piece of paper, later you can try it. And you use a chopstick, you punch 2 holes. Okay, try to imagine, this is a paper. Okay, so then you use a chopstick. Punch 1 hole like this. Oops, sorry. Okay, the second chopstick. Okay, okay, imagine. And then now, initially nothing. So you can see that the piece of paper still remains straight, right? Okay, but now you tight rubber band. You tight rubber band. And here. So with tight rubber bands, what will happen? You can see that rubber band is something like the hydrogen bonds that actually make the distance shorter here, right? The distance becomes shorter. So at the end, you can see that now your paper tends to bend. Can you see that? And then the chopstick will be the shape something like this. Because of the extra force here, the rubber band. So same goes to this molecule. Try to imagine this molecule. They will turn, they will curve. Why? Because shorter distance. Why? Because the attraction force, additional attraction force of the hydrogen bond. So this kind of hydrogen bond is termed as intramolecular hydrogen bonds. Okay, so this kind of hydrogen bond is termed as intramolecular. I will tell you guys why. Hydrogen bond. Are you clear? So look at this, guys. So this is carbon number 4, carbon number 1, 1,4, alpha 1,4 glycosidic bond, alpha 1,4, alpha 1,4, alpha 1,4. Because alpha 1,4, you make the OH and H side by side, OH and H side by side, OH and H side by side. Okay, so in this case, H is delta positive, O is delta negative, therefore they form hydrogen bond. So this is one molecule of amylose. So intra means within. When you use the word intra means within. So it's within, right? This hydrogen bond actually formed within one molecule of amylose. So this hydrogen bond is termed as intramolecular hydrogen bond. It will make this amylose molecule turn into the helical shape. Continue. And this helical shape make this amylose become very, very compact. Are you clear? So 1,000 of them packed together. And again, amylose molecule, guys, as we know that amylose molecules, they are insoluble in water, therefore they won't cause or they won't lower down the water potentials of the cells. Okay. Now, how about amylopeptin? Amylopeptin is a branch molecule. Now, it's a branch molecule, again consists of alpha glucose. Okay. And then you can see that the unbranched change of alpha glucose still the unbranched. Okay, this is unbranched, right? This part is unbranched, right? This is unbranched. So the unbranched here, can I see that? The unbranched here. Okay. So what will happen here is, look at this. This unbranched one is still carbon number 1, carbon number 4, carbon number 1, carbon number 4, 1, 4, 1, 4. So this is alpha 1, 4 glycosidic bonds. Can I see that? Alpha 1, 4. But when you want to join one chain to another chain, can you see that? First change to second change, this is carbon number 1. This is carbon 1, 2, 3, 4, 5, and 6. So we're going to join carbon number 1 with carbon number 6. So this one is alpha 1, 6 glycosidic bond. So the functions of alpha 1, 6 is to make or to link two chains together. Can I see that? Two chains, we want to link them together. We use alpha 1, 6 glycosidic bonds. Okay, so the title of this question is wrong. We are not talking about the hydrogen bonds. We are talking about, change it, guys, glycosidic bond. My mistakes. Okay, change it to glycosidic bonds in amylopeptins molecules. So again, you can see that we want to label alpha 1, 4 and alpha 1, 6. So this one actually is alpha 1, 4. Red color, alpha 1, 4. Whereas alpha 1, 6, I use the blue color. This is alpha 1, 6. Okay, glycosidic bond. So I'm going to show you guys how the alpha 1, 6 glycosidic bonds can be formed later. Okay. So now you should know where is alpha 1, 4. So alpha 1, 4 always form. Okay, so where is side by side to form this unbranched change. Are you clear? Alpha 1, 4 is unbranched change. Okay, and alpha 1, 6 is the one that join two or branches, or join the branches together. Okay, so come back to our notes here. So just now we said that the unbranched chains of the alpha glucose are held by alpha 1, 4 glycosidic linkage, but the branch are joined by alpha 1, 6 glycosidic linkage. Okay. I'm going to draw two chains. Okay, a simplified one. Okay, so this is one chain. So this is carbon number 6. So carbon number 6 OH groups here. Carbon number 6, carbon number 1. So this is carbon number 1, carbon number 2, carbon number 3, carbon number 4, carbon number 5, carbon number 6 outside the ring. Okay, carbon number 6. So against carbon 1, carbon 2, carbon 3, 4, 5, and carbon number 6. So against this part is the alpha 1, 4 glycosidic bonds. Okay. Okay, now, so now look at this. If I have any extra one chain here, Draw it down a bit. Okay. Not so nice. Okay. Can I? Okay, this is another change. Okay, it's incomplete one. Okay, can you see that? Incomplete. So here, what you can see that this is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. Carbon 6 is CH2. OH, cannot. We'll keep on saying that CH2 OH cannot. Can you see that? Okay. So what will happen here is one donate hydrogen atom, another one donates oxygen, release oxygen. OH group. One is H, one is OH. So it means that we can remove these as H2O. Can you see that? We remove it as H2O. So once we remove it as H2O already, so I remove here, guys. So what you can do? We can join both together now. Okay, so when you remove it as H2O, can you see that? I can join them together. So again, guys, can you see that? C, O, C. So this COC is termed as glycosidic bond because we join carbon 1 and carbon 6 cannot. So, and also alpha glucose, so it's alpha 1,6 glycosidic bond. So therefore, can you see that now, guys? We join both together. So can you see that this one chain, another chain? So two chains can be joined together through alpha 1,6 glycosidic bond. So here we can have another chain. So it means that we can have many chains actually joined to one chain. But when we want to join the branches together, they must use alpha 1,6 glycosidic bond. Okay. So the next polysaccharides after the starch, we're going to look at this glycogen. Glycogen again highlights they are also made from alpha glucose. In terms of structure, they are very similar to amylopeptin, but they tend to have even more branches than amylopeptin. So if you draw it out, the structure, amylose, amylopeptin, how about glycogen? More branches, shorter branch. So what is the benefits of having this? Again, two sides for the enzyme attachment. This one, can you see that? Okay, compared to the glycogen. If you compare to the glycogen even have more branches, so it means that more site of attachment for the enzyme. So more enzyme can attach. So therefore, in terms of the rate of hydrolysis, this one will be low, this one will be moderate, and this one will be very high. Because if you look at where we store, glycogen is stored in animal. Okay, animal cells, primarily in the liver and also the muscle cells. Those are very active cells that require high supply of the glucose. So we cannot wait slowly. Okay, now we wait slowly to hydrolyze my amylose so that to provide the cells with the glucose. Too slow. The liver cell and muscle cell cannot sustain in this case. They cannot. Okay, so that's why they don't store in amylopeptin. Why? If you store amylopeptin, also a bit moderate in terms of rate of hydrolysis, not fast enough in the process. Therefore, we store glycogens in the liver as well as muscle cells. Why? Because more branches, more site of attachment for the enzyme to break down the glycogen. So to supply us with the glucose will be used for the respiration. Okay. So if you look at the glycogens compared just now, okay. So not so branch, right? Not so many branches. Can you see that? But if you compare in this diagram, is okay. So you can see many branches join together. So how they join? So when the branch they join by 1,6, okay, alpha 1,6 glycosidic bonds. But the straight one continue. If continue like this, okay. So the chain, the unbranched chain, those glucose molecules, they are joined by alpha 1,4 glycosidic bonds. Okay, so with this, I've done parts of this polysaccharide. So we have settled for the starch and glycogen. So